Now, we need to do a bit of number theory here. Natural numbers. Natural numbers. There are numbers such as 1, 2, 3, and so on. 7. So I think we can include 0. I'm not so sure about that, but let's say we can. Integers, they are pretty much the same, except that we include the negative one as well. Negative 5, negative 3, and the natural number as well. So 1, 2, 10, and so on. So this sets of natural numbers, it's called n with a double bar at the front, and the sets of integers is called z with a double bar like this. Then we have what's called the rational numbers. And these are numbers such as, for example, 3/2, or 7/5. And then the negative one as well, minus 9/4. These ones, and so on. These ones, the sets of rational numbers is called Q for quotient. Now, obviously, N is for natural. Z, well, I think it's from some German words. Okay. What about the numbers that looks like this? 1.6. Well, 1.6, it's the same as 16 divided by 10, which we can simplify is what? 8/5. So therefore, all of these numbers, all of the decimals are rational numbers. Now, what about the numbers that are such as, for example, 1.333 infinitely, so basically which we write 1.3 with a little dot on it to say they are recurrent decimal. Right. What is that? Is that an irrational number? Well, this is what I'm going to do. I'm going to call this number x here. If I do 10x, well, I'm sure you would agree that it's 13.33333. Now, if I subtract 10x minus x, that 10x minus x, well, that's 9x, of course, but it's a 13.333 minus 1.33, and this, not too difficult, it's actually 12. So therefore, 9x equal to 12. Well, so that means that x is equal to 12/9, which simplify as 4/3. So that means that 1.3 recurrent is equal to 4/3. Well, that means that basically this recurrent decimal is actually a rational number. So I'm going to write that. You know what? Let's do another example with a bit more complex recurrent decimal. Oopsie. Say we have 5.12, which can be written as 5.12. And then we would like to write it as, to see if it can be written as rational number. Well, what I'm going to do is I'm going to write not 10x, but 100x. So that 100x would be 512.2 recurring, whereas 10x would be 51.2 recurring. Right, well, what I can do is if I do 100x minus 10x, which is 90x, Well, that would be 512.2 recurring minus 51.2 recurring, which would be, if I plug that in my calculator, 461. Therefore, 90x is equal to 461, which means that x is equal to 461 over 90, 461 over 90, which actually doesn't simplify, is as is. So, right. So, okay, I've demonstrated again that 5.12 recurring can be written as a fraction. Well, a bit of a push. Basically, all recurrent decimals can be written as a rational, as a fraction. So are rational numbers. It's an important thing. Right, now let's talk about numbers that cannot be written as a fraction. And this, for example, are numbers such as root 2. Root 2, if you plug that in the calculator, you get approximately 1.14, and then it keeps going. It never repeats, does not repeat. Well, likewise, root 3, it's equal to 1.732, and then doesn't repeat. They are not rational numbers. They cannot be written as fraction. Now, there is a proof of that. It's a proof that's done in extension 2. It's not that difficult, but I'm not going to do it here. Likewise, numbers such as pi, which is approximately 3.1415, and keep going, again, doesn't repeat, not rational number. There are plenty of numbers like that. So anyway, if I, and these numbers which are not rational, they are part of the set of real numbers. Now you may say, oh, how come they are called real? They are numbers, no? Well, in extension 2, you will learn that there are other numbers which, such as, for example, we define a number called I, and such as I square is equal to -1. That sounds a bit weird, but these ones are called imaginary number. I'm not going to get too much into it. They do not exist in real life, but they have real applications. Sorry, physical applications, should I say, but we're not going to talk about those. Anyway, all of that to say, if I symbolize the sets of numbers, so there is the sets of natural number, the sets of integers is includes the natural number, and then there is the set of rational number, and then inside that is a set of real numbers, and that symbolizes basically how these numbers are part of each other. Okay, now let's move to another topic, which is surds. So things like root 2, this is called a surd. Now, what are surds? Well, say for example, if you have root a times root a, well, that's equal by definition to a. Now, okay, so for example, root 3 times root 3, it's equal to 3. Now you may say, well, okay, so likewise, if we have, well, what is root 9, for example? Root 9 is a number such as 3 times 3, sorry, root 9 equal 3 because 3 times 3 equal 9. But you're going to say, okay, well, but hang on. Root 9 could also be equal to minus 3 because minus 3 times minus 3 is also equal to 9. But no, we have decided that the roots of numbers is always positive, so we don't look at the negative ones. Right. So now, root of A times root of B. Well, okay. So if I just take the square root of that, the square of that, that's what? That's square root of A times square root of B times square root of A times square root of B, which we can swap the middle terms. So that's square root of A times square root of A times square root of B times square root of B. So therefore, it's A times B. Now, what about square root of AB square? Well, again, that's square root of AB times square root of AB, which by definition is AB. So therefore we must have, I'm just going to change color, we have root of A, root of B square, because these two quantities are equal, which is equal to root of AB square. And because we know the square roots are always positive, that means that the square root of A times the square root of B must be equal to the square root of AB. Okay, well, that's going to help us to simplify a bit some fractions, some thirds. Say, for example, we want to simplify square root of 12. Well, square root of 12, that is equal to square root of 4 times 3, which is square root of 4 is 2 square times 3, which basically using what I've demonstrated above, 2 square times 3, and this, by definition of the square root, is just 2. So therefore it can simplify as 2 root 3. Let's simplify another one. Simplify root of 80. Okay. So I could just try to find the decomposition in prime factor, but there is a function on the calculator which is called fact, and that helps you to find the decomposition in prime factor. And this on the calculator is going to tell me this is actually equal to 2 power 4 times 5. So therefore it's equal to root of 2 power 4 times root of 5, which means that it's 4 times root 5. Okay, we can okay, well, let's do another one. Simplify 4 root 2 times root of 24. So we're just 4 root 2, there is not much we can do, so we're going to leave it like that. Root of 24, 4, if we do, that's root of 2 power 3 times 3, which is therefore 4 root 2 times 2 root 6. And so it's equal to, okay, so 4 times 2 times root 12, which is therefore 8 times root 12, and using the same reasoning than what I've done above, root 12, I found it's 2 root 3, so therefore it's 8 times 2, 16 root 3. Yes, and I cannot go any further, it's fully simplified. Now, finally, we are going to look at rationalizing denominator. Denominators with thirds. Okay, so for example, I have 6 over root 3. And we want to rationalize the denominator. Why do we want to do that? Well, sometimes it's just helps to simplify fractions. So I want to get rid of the root 3, which is at the denominator here, which I'm just going to do here, this one. I want to get rid of that. The best way to do that is to actually to times the denominator by root 3. So I'm going to time, obviously, if I times the denominator by root 3, I also need to times the numerator by root 3. So it's 6 times root 3 over root 3 times root 3. So, okay, the numerator now 6 root 3, and the denominator is root 3 times root 3, 3. Then I've got 6 over 3, which I can simplify. It's 2 over root 3. There you go. Let's do another one. Root 60 over 3 root 6. Okay, so we need to simplify. 60, it's what? It's 6 times 10. If I kind of look for the prime decomposition of 60, that's 2 root 2 square, sorry, times 3 times 5 over 3 root 6. So that's equal to 2 times root 15 over 3 times root 6. Okay, so I'm going to time by root 6 to get rid of the root 6 as the denominator. So it's 2 times root 15 root 6 over 3 times root 6 root 6, which is equal to 2 times root, that's what, 90 over 3 times 6, which is 18. So therefore it's equal to 2 times 3 squared times 10 over 18, which, so it's actually root 3 squared times 10 over 9, which is 3 root 10 over 3 over 9, sorry, which is root 10 over 3. Here we go, fully simplified.